about talk about sensors. Last time we talked about this the devices, logic devices, and we have two different categories of logic devices. One is called the combinational logic device. Second one is a sequential logic device. And I asked you guys to pay more attention to the XOR, which is a gate, which is a new database, new knowledge database. And then we continue to talk of sensors. I talked to you about the sensors and the transducer. And sensor is a complete is a component that can detect magnitude of physical quantities. The transducer is an active element of the sensor. So this is the difference between these two concepts. And however, some professors, some researchers, they just say the transducers is sensors. I'm okay with you that one. Okay, but this is the common understanding of these. I'm actually not saying common understanding. This is one version of understanding of these sensor and the transducer. They are kind of different. The transducer is active component of sensor. However, if you say sensor is transducer, absolutely fine. I will not argue with you guys. So then the sensor, when you select a sensor, I know you are doing this is the senior design, right? Have you formed the group teams already? Or you are doing now? You formed the team already. That's cool. So if your team is going to do some mechatronic system design, and so you will have this task. And first one is select the sensors, right? So select sensor. When you select sensor, you need to know your what kind of functionalities and you want these sensors to accomplish for you. So when you when you select the sensor, and there are several these characteristics you need to keep in mind, and for any sensor you want to select. First one is the transfer function, and the transfer function actually is a relationship between the physical signal and this measurement and the signal you want to measure, and the electrical output signal. So this is the transfer function. And this is the fact sheet. This is a technical sheet for any sensors. So you can take a look at that one. So sensitivity, the ratio between a change in output electrical signal and to a given change in the input signal, physical signal. So this is sensitivity. So how sensitive your sensor is. So it's talking about that is the sensitivity. So span or dynamic range, the range of input of physical signals which may be converted to electrical signals by the sensor. So this is span or dynamic range. This range, outside this range, and your sensor will not be working for your purpose, for your function, or for your task. Okay, you need to be very, very careful. You need to know what is the span or dynamic range and you want your sensor to work. The signals you want to detect, and you need to know the range. And then you select appropriate sensor that can accommodate this span or dynamic range. Otherwise, it's not working very well. So the next one is accuracy. The accuracy is very easy to understand, and the largest expected error between actual and ideal output signal. So this accuracy. Nonlinearity. So nonlinearity, we know nonlinearity in mechanics. Here is also, we use this word, this concept, nonlinearity. The maximum deviation from a linear transfer function over the specified dynamic range. So this is nonlinearity. Okay? So hysteresis. Now hysteresis is a very, very important concept. I want you guys to know what this hysteresis is. And hysteresis in the mechanics, it says that if you load a starter and then unload it, you can see the loading history and the loading parts and the unloading parts are distinct. So this is called hysteresis. Right? But also here, and in this signal processing, I will also have this idea on hysteresis. Hysteresis in here you can see this is a mirror band. So this is your signal output. If you increase this one, you can see this signal output and going up and down. So these are two parts, they are distinct. Okay.
Is the resist like a lagging?
Then what?
Like a lag. Like you have like
not really, but it's not really. So these are two different parts. So in the mechanics, the hysteresis is always accompanied by heat and heat dissipation. But for this signal, so that means this is so these are two parts and they are different and they are distinct. Ideally, okay, ideally, so these two parts should be the same, at least for mechanics. For mechanics, if these parts and they are the same, it means that my material can recover exactly. But here, no. Actually, no. But sometimes in the metal, and this is commonly used materials, we just ignore this hysteresis. But actually, we have any material, they have some hysteresis. So, as I said, this idea is applied to signal processing. So, and you should be able to use your own words to tell people what is the hysteresis is in signal processing the realm. Right? Maybe you, when you get an interview and some people ask you about the hysteresis in the mechanics, and you can still tell people draw them up and tell you this. Noise. Noise, all sensors produce some output noise. Noise is some background noise. Resolution, the minimum detectable change in the measured quantity. So if this resolution is very small of the sensor, that's good. Okay. The bandwidth, the range of frequencies of input physical signal that a sensor can detect. So all these characteristics, and you need to take care of, you need to consider when you select a sensor. Right? But mainly you focus on this transfer, sensitivity, span range, and also this is accuracy. So all these things you need to think about this one and to make sure this sensor is cost effective and it also can fulfill your purpose and can accomplish your goals. So question regarding this the characteristics you need to take care of when you select a sensor. Okay, no question. So what I want you to pay more attention is to this one. If we are giving you a figure, I will ask you in the signal processing or the mechanics realm, and this phenomena is called what? Or I just ask you, use your own language to tell me what hysteresis is. And then we talk about several specific sensors. First one is the shout encoder. The shout encoder, you can see as the name suggests, is attached, is mounted on a shaft to measure something. What they are going to measure? They are going to measure the angular rotation. So one of the most common brake beam sensor is the shout. So the shout sense encoder. I will shout encoder first. shaft encoder. This is a brake beam sensors. Is a shaft encoder on a motor. Okay, so it is used to measure the angular rotation of the shaft or the axle. So they provide the position and or velocity information about the shaft, and they are connecting to. So this is like a speedometer or the odometer. So how fast it rotates and how much angle they rotate. Position and velocity information from encoders can be used to drive the rover a certain distance or a certain angle. So you can specify this is the angle or the distance you want to drive the shaft. And so these movements will not be precise because the slip and slide and backlash in the gearing mechanism. So this is shaft encoders, these most movements. They are okay, the precision is okay, but it's not very accurate. It's not very precise. Okay? So if you want to have very precise movement control, and don't use this one. And so, any questions regarding this slide? So we have learned this backlash, right? So who can tell me what backlash is? Well,
there's a little bit of a movement like in the gears before it actually starts turning, and then you get an inaccurate reading on the scale compared to it actually moving.
Yeah. This is a backlash. Backlash is the result of the manufacturing the efficiency. Okay, so these are two gears. They are not meeting precisely. There's some clearance on one end. If you just turn in the opposite direction, and you need to compensate this clearance first. That's what the backlash. You understand, Sarah? So, by the way, this spring, I did not teach you the machine design, right? Or they told you, right? Did he mention this backlash? No?
They did.
Okay, good. Okay, the gear. Usually when I teach the machine design, when I talk about the gears, and I talk about this backlash. So these are shaft encoders. Next one is the heading sensors. So heading sensors can be perceptive or this gyroscope, this inclinometer or accelerometer for exoceptive. This is a compass. So this is, as the name suggests, so this is gyroscope, inclinometer, accelerometer, and this is the exteroceptive. So this is a compass. So this is sensors, and they are used to determine the rover's orientation and inclination. Orientation and inclination rovers. You can, if you want, this is sensors on these rovers, and they may be used with appropriate velocity information to integrate the movement to a position estimation. For example, that reckoning is a sleep navigation. So this is the handling sensor. So we have these handling sensors. This is in my office, and as I told you guys, so previously 7 years ago, and in this class, we incorporated this is the autonomous rovers in our course, but finally we just stopped teaching that part. So we still have some the important. This is the sensors in the office. So next one, it appears twice. The compass. When we talk about the compass, compass. The compass uses the Earth's magnetic field to determine the absolute measurement for the rover's orientation. So this is the orientation of the rover. So a large variety of solutions to measure the Earth's magnetic field, and there are several ways. We have this is magnetic field. The Earth has very weak magnetic field. So they use mechanical magnetic compass. So this is the first category, and second category is magnetometers. So also, so it is used to measure the magnetic field. Direct measurement of the magnetic field. This is the three solutions to measure the Earth's magnetic field. So this is a package of the compass. So the major drawbacks. So these major drawbacks. The first one is the Earth's magnetic field is usually very, very weak and easily distributed by magnetic objects or other sources just nearby. So bandwidth limitation of electronic complexes and susceptibility to vibration. So not feasible for indoor environment. So this is compass. We have different kinds of compass in the market. So this they have some drawbacks. When you select this compass, and you need to be very, very careful. It's always so initial sensors. So initial sensors. So first one is a gyroscope. Gyroscopes. So measure the rate of rotation. Independent of the coordinated frame. So this is very, very important. Second one is it uses the principle of conservation of angular momentum. So whenever you design your sensors, you must follow some physical principles. So common applications for the gyroscope on heading sensors on full inertial navigation systems. So accelerometer measures accelerations with respect to inertial frame. So the common applications of accelerometers include Q sensor in static application, vibration analysis, and full. This is the INS system. If you have in your measurement course, have you ever used these accelerometers, guys? Have you ever used? Or no? Yes or no? No? Okay. So this accelerometer is very, very important one. This is gyroscope. So this device return a signal proportional to the rotational velocity. So this is a package, and you can buy this gyroscope from this website. So there is a large variety of gyroscopes that are based upon different principles. Gyroscopes are heading sensors that keep their orientation in relation to a fixed frame. And so it provides absolute measure for the heading of a mobile robot. And there are mechanical and optical gyroscopes. So mechanical gyroscope and the relatively is very cheap. Optical is more expensive. So mechanical gyroscopes they use the standard gyro, relies on the standard properties of a fast spinning rotor, and rated gyro. It measures angular speeds instead of absolute orientation. So regarding the optical gyroscopes, they use light beams or lasers instead of mechanical parts and measure angular speed. And so these optical gyroscopes, and usually they are very, very precise, but you need to pay more money to buy this optical gyroscope. So you can try these two websites to see if you can get what kind of gyroscopes you have and now currently. So here is this is the orientation. Okay, how this give you is the show you and how it do the orientation angle. So we have rotation rate, and then we do the integration, and then finally we have this orientation angle. So there is one principle. There is one sum of rule. If you use the integration or derivative for any is quantity, and the precision is not good. Right? You understand, guys? If this angle, if this output is not the output is not a quantity you measure based on the principle directly, the result is not accurate, not very accurate. Because you are doing something. For example, rotation rate. We measure this one directly. And then we do the integration. And during the process of integration, some errors will be ended. Right? So this is that's the result orientation angle, and it's not as accurate as rotation rate. So this is the sum of root. Accelerometer. Then we talk about accelerometer. So this is used to measure the accelerations. And they measure the inertial acceleration is inertial. F equals ma, force equals the mass multiplied by acceleration. And they measure the inertial force generated when mass is affected by a change in velocity. So here they use that is the frame. That is usually how this is accelerometer works. So we have the frame, we have damper, we have mass, and we have a spring. So this force may change the tension of the string, okay, actually the spring, the deflectional beam, the vibrating frequency of S. And they use this one, this equation. We know the force equals ma multiplied by damping coefficient divided by multiplied by the velocity, and equals k is the spring constant, x is the deflection. So this is the total force equals this one. So because we know C and we also know this one, we know K and we know deflection. And using if we measure the F, and then we can calculate this M multiplied by this A. Because M is fixed, and we can calculate, and this is the acceleration. So this is how it works. The main elements are mass, suspension mechanism, and sensing elevator element. High-quality accelerometers include a servo loop to improve linearity of the sensor. What is a servo? And so we will talk about servo. We will talk about servo in detail when we talk about the actuator. And the loop is control. This is control algorithm. This is a loop control. And we are going to talk about this one after we finish the sensor. So the application. Always I need to click it twice. Accelerometer, the application. So they can be used to sense orientation, vibration, and shocks. Whenever this the acceleration is involved, and you can because the sensing the orientation when this is robot is rotating, the orientation is changing. If the orientation is changing, that means acceleration is changing. You agree? Even though this is the magnitude of the speed does not change, but in this case rotating, but still the force is a force. If you have a force, and you must have about acceleration. So this is the orientation change, vibration, and vibration definitely is acceleration. So shocks is the acceleration also. So usually in electronics, flash items for user input. So acceleration integrated once gives the velocity. Okay, if you have acceleration and you integrate it once, and you will get a velocity, and then you integrate again, and you will get a position. As I said, the sum rule is that if we want to measure the velocity, I usually use a sensor that uses the principle measuring the velocity directly for precision. If you want to measure the position, and you need to use a sensor that measure position directly to get high precision. Why? Because if you do the integration or derivative, you will always lose some precision. So the integration process is not precise and introduces error into the velocity calculation. This is what I just told you. So global positioning system, and so we use this one. GPS, we use GPS every day, almost every day. At least I use GPS whenever I have a long distance trip. So the GPS revolutionized the modern navigation technology. So extremely effective and one of the key sensors for outdoor mobile rovers. So 24 GPS satellites are available at all times for civilian navigation. For the military, it's more. This is the satellites. Passive external-sensitive sensors, triangulation of 3 data points, and help the receiver infer its own position. Triangulation of 3 data points. So major drawback with the use of the beacons indoors. The beacon requires change in the environment and limited flexibility and adaptability to change environments. And then we talk about the Hall effect, these sensors. And so this is the Hall is the engineer's name. So it is Eddie Hall, right? So this is Eddie Hall. So this one is used to these sensors provide non-detect means to detect and measure a magnetic field. So this named based on the use of their Hall effect, discovered by Edwin Hall in 1879. This is very this is many years ago. To measure, it is used to measure the magnetic field. So how it works? Here, this is the principle. And suppose we have this is the permanent magnetic field. These are 2 poles, North Pole and South Pole. And so presence of magnetic field deflects electrons flowing through a conductive material. So suppose this is a battery. So here is a conductive material. So here is a path. If you have this is magnetic field here, and so this is the field will deflect electrons flowing through this path. So as electrons move to one end of a conductive material, a potential is developed in the direction. So perpendicular to is a cross current flow. So here, and so this potential indicates the strength of the magnetic field. So if you have a potential here, and you know there is a magnetic field, and the magnetic field, the magnitude of magnetic field, and shows the higher potential in these parts. So applications of Hall effect sensor. First one is IC, is engine electronic ignition system, and used to determine the position of camshaft. And brushless DC motor control. And we are going to talk about this one in detail as one of the most important. This is actuator, brushless DC motor control. Assembly lines to determine the shaft position and velocity sensors, and contactless limit switches, the current sensing ICs, integrated circuits, electrically isolated alternative to shunt resistors. So there are 3 different types of Hall effects. The types. The first one is a linear Hall effect sensors. Second one is a Hall effect digital switches. The third category is Hall effect digital latches. So for first category, the output is proportional to magnetic field strength, and as the name suggests, linear Hall effect sensors. Second one, so these are digital switches. The presence of field above threshold and turns switch on. A presence of field below threshold and turn the switch off. It's just like a 2-value. This is a 2-value switch. So Hall effect digital latches. North field turns latch on, and south field turns latch off. So these are 3 different categories. So here are the packagings and manufacturers for this oil fed sensor. ICs, analog devices, electro microsystems. They have this kind of this is the products and packaged units, Honeywell, and many more. So you can just, here are two websites if you are interested, and you can just explore a little bit more. I don't know where you can find again. Then we talk about the variable reluctance sensors. So this is another sensors that are commonly used in the industry, in the manufacturing country, manufacturing automation. So these sensors are used to measure speed. That one is used to measure this magnetic field and the position of moving metallic objects. So this is a sense the change of magnetic reluctance, which is analogous to electrical resistance near the sensing element. So we require conditioning circuitry to yield a useful signal, because sometimes this original signal, the raw signal is very weak. So you might use either to have a conditioning circuitry to yield a useful signal. So here is a website. This is a variable reluctance sensors. So how these variable reluctance sensors work, and whenever you have a sensor, you must show you what is the working principle. So for here, magnet in the sensors creates a magnetic field, and we have a magnet here. As a ferrous object moves by the sensor, and the resulting change in the magnetic flux induces EMF in the pickup coil. So EMF stands for electromotive force voltage. Can write down this? EMF stands for electromotive force voltage. EMF is called electromotive force. It is named the force, but it is a voltage. It's a kind of misleading, but it is called this electromotive force voltage. EMF is whatever. So maybe you have already known that magnetic field and electric field, and they are two sides of one coil. You agree? So these two guys are always together. If you have electricity flowing on, and you always have magnetic field. If you have magnetic field, something is moving in the magnetic field, you will have electricity. You agree, guys? Electrical, magnetic, and these two words are always together, and they are the two sides of the same coil. EMF means that whenever it is a magnetic field, okay, if we have a magnetic field, there is a conductive wire or this loop. If this wire is moving, and you will have the electrical voltage. So this is called EMF. EMF is called force, electric force, but actually it's getting voltage. Can you write down? I will test you again. Use your own words, tell me what is EMF is. See, whenever, if you suppose we have a magnetic field, whenever we have a ferrous object moving by the sensor in the magnetic field, and you will have some potential, electrical potential, and in the wire, and this potential is called EMF. It's not just for this one, for anything in the universe. So typical configuration, suppose this is the target here, and this is the sensor, this is the gap, and so this will be the output. This output is the magnitude of your EMF, and the sensor will measure the potential to know how big the distance is. Okay, because the distance is determined by determines the magnetic field. And typical application of this is the variable reluctance sensor. So the shaft velocity sensor for ABS, the traction control. This ABS is automatic braking system. So do you guys know ABS? Maybe you do not know this one. This one is not a very big word for you guys because you are new generation. For me, older generation, ABS is a very, very advanced, was a very, very advanced technology 25 years. But for you guys, it's just daily life. It should be there. Otherwise, this is not we will not get the car. The crank and the camshaft position sensors. So they can use the sensor schematic, the distance, measure distance. So here's a gear. And so here's how it works, and you can go to this website to see how it works. Installed on a CV is axle to measure the shaft velocity. So then we talk about the sound navigation and reading on the sonar. The sonar is a very, very interesting. This is the sensors. It uses ultrasound and refers to the range of the frequencies of sound that we cannot hear. Okay, we cannot hear. The process of finding your location based upon sonar is echolocation. Echolocation. What is the echolocation? So this sensor sends out the sound out, and then if the sonar signal encounters some obstacles, then this is the sonar. The signal will be bounced back, right? Then this sensor captures the signal that is bounced back, and then know whether there is an object or not, or whether there is an obstacle or not, and how big is the obstacle, how far it is. And sonar are active sensors that emit a chirp or ping and use time of flight to determine the distance. The transducer on the sonar emits the chip and ping and receives the sonar echo that comes back. Mechanical energy is converted into sound as the memory on the transducer flexes and to produce a ping. So this is how it works. So this is active. It's called an active sensor because this sensor keeps emitting. This is the signal. Whenever there is an obstacle, and so this signal will be bounced back, and then this sensor will calculate how far the obstacle is and how big the obstacle is. Let me ask you guys. And usually we know two animals and use the sonar to locate, echolocate things, the food or the enemies. What are they? Huh? Yeah, that is one. Dolphin. The dolphin. Whale is also. Doesn't the food whale? I don't know. But I'm a dolphin. I'm talking and this is bad. Okay. So some applications. So suppose we have Robert, and if we put this one in the context of Robert, and we have Robert, and indoors in the room, we have a chair here. So this Robert has a sonar is the source, and this guy will emit the sonar signal in all directions. However, here's the door. Suppose the door is open. So here it is take a long time to receive the bounce back, receive the signal back. Maybe there's no come back at all. So let's know that here is the door. So but here, based on the flight time of the signal, and this rover know how far it is from here to the rover, how far it is from here to the rover, and also how far the chair is, and also how big the chair is. So advantages and disadvantages of the sonar. So advantages: reliable with good precision, not as prone to outside interference. So it is not in the outside interference. Why? Because the outside usually, if the space is very open, and you cannot receive the signal back at all. So good maximum range, inexpensive. This is relatively cheap. And disadvantage: sensitive to the smoothness. Sensitive to the smoothness. If the surface of the target is very smooth, they cannot. Maybe there is no reflection, or the reflection will come back. The sensitive to angle to obstacles, or angle, because it will go this way. It's almost like a mirror reflection. It go this way and bounce back the other way. On poor resolution, I'm prone to self-interference from echoes from different directions. The echo spike it might have self-interference. Cannot detect obstacles too close. If too close is a problem. Solve the surface of a solid sound energy. So this can be used in some solid surface, and you cannot detect. This sonar cannot detect. So here are the advantages. So we talk about laser range balance. So laser, they use laser for distance and range measurement. And laser emit and highly is amplified and coherent radiation at one or more frequencies. And it may or may not be in the visible spectrum, depends on your laser system. And laser is also used the time of flight principle. Send out the laser and function by, and then I know the time, right? The time of the distance, the in flight, and then calculate distance. They are much faster than sonar because the speed of light is much faster than the speed of sound. And laser is light. Remember that one. Laser is a light. It's spectralized light. And lasers are the most accurate sensors for measuring distance up to now. And similar to this IR, light is emitted and detected. This unlike sonar, light is projected in a beam rather than a cone. So this is a beam rather than a cone. The sonar is a cone here, cone back. But the laser is a beam. It's very concentrated beam. Right? So the sensors are lighter, or lidar system. So the light detection and reading system. So advantages for this laser, the better resolution than ultrasonic, infrared, and cameras, very reliable, not as sensitive to listening conditions as cameras and infrared. And for mapping, lasers are high quality 3D versions of IR sensors. So disadvantage: cannot identify mirrors and/or glasses. Why? Because the mirror and glasses reflect. Be very careful. If you want to use laser to measure some laser, be very careful. You may damage yourself. More expensive than all other sensors, larger and heavier than all other sensors. Why is it larger and heavier? Because there is a laser generator. Okay. So these are pretty much and the proximity sensor, and we will use the proximity sensor. Proximity sensor means that if you put your hands here and the proximity sensor detects the existence of something and then say yes or no, we will use